Okay, hello everyone. Welcome back to the Intercontinental Seminar Series on gravity and cosmology. So today it's our big pleasure to have Professor Vitor Cardoso as our speaker. Professor Cardoso got his PhD in the Instituto Superior Técnico in Portugal in 2003, and right now he's working in Niels Bohr Institute and a distinguished professor at IST. And as many of you already know, he is one of the leading experts in the field of gravitational physics and black hole physics. So today he's going to talk about black hole spectroscopy. And so during the talk, if you have any questions, so just please feel free to raise your hands and I'm going to allow you to ask questions. So without further ado, then please, Vito, the stage is yours.
Thank you, Chaeyu. Hello, everybody. First of all, it's a really great pleasure to be speaking to you. I think it's a wonderful initiative, but it's also the right time to do that. We have, as you may know, new instruments. We're entering a new era in gravitational physics, and I'm sure that the next years and decades will bring a lot of surprises. So it's important to discuss ideas, to discuss how to move forward and what's going on in the field. And that's exactly what I'm going to try to do. So we understand gravity, or we think we understand gravity really well. And we've tested it very carefully. We tested it on scales and weak fields, such as the ones probed by this child over here. He's jumping somewhere on Earth, and we understand exactly how gravity behaves on those scales and on gravitational potentials that are weak enough. But now we also have access to regions in the universe where gravity is extremely dynamic and where it's extremely intense if you measure it by some version of the Newtonian potential. So it reaches potentials of order 1. But it can vary on very short time scales immensely. And so do we understand those regions? Do we understand those regimes? So I'm going to talk exactly about that. How can we test regions where gravity is so intense? And of course, regions like those are known as black hole spacetimes. And there's at least 2 extremely appealing reasons to understand, to study black holes. One of them is related to the singularity results by Penrose and others that say that whenever you have the formation of a trapped surface, so whenever you have an apparent horizon in the universe, then something goes wrong in the inside of that region. Either because your notion of energy goes a bit crazy, goes a bit berserk, or the field equations are violated, or even you lose the concept of a smooth manifold, of a smooth space-time. And there's ways of trying to save us from this, but they're really just conjectures, okay? So the mathematical theorem is something in our classical equations goes wrong in the interior of black hole spacetimes. So if there's anything in physics that we know it has room for progress, then really it's general relativity and black hole interiors. We need to understand that. We need to complete our knowledge of black holes. Fortunately, and this is where the second piece comes in, we were given kind of a beautiful and mysterious property of black hole spacetimes, which is the uniqueness theorem. And that states that in vacuum, any stationary and asymptotically flat black hole solution belongs to this family over here, the Kerr family of black holes. So I set Newton's constant and the speed of light to 1. And if you look at this line element, it only has 2 parameters, the spin A and the mass M. quantities that you can measure far away from this object. Okay, so any black hole that's sufficiently well isolated should be characterized by these two quantities. Really, it's an amazing gift that we were given. By the way, please just interrupt me or send messages on the chat if you think I'm saying something stupid or if you have a question. Really, it's supposed to be an interaction and an exchange of ideas. Okay, so this means that in principle, at least stationary black holes really are kind of an ideal object to search for new physics, but also to test what we think about our ideas about general relativity. Now it turns out that there's yet
Sorry,
another gift.
Vitor.
Yeah.
I think
Oh, hi, Aaron.
Aaron has a question.
Hi, Vitor. Just quickly on what you said, because the fact that or you made the statement that all black holes in the universe are described if they are sufficiently isolated by this solution, but that's only true for the exterior, right? We don't really know what happens in the interior if something is generated by a star or something like that, right?
Yeah, that's a wonderful point. So my statement only concerns the black hole exterior, which is the part we can have access to. But of course, I think, as I was saying, we really need to complete our knowledge about the black hole interior. And we really have, well, there's plenty of ideas, but there's no single consistent framework that we can use for that. But yes, thank you, Aaron. That's totally correct.
Perfect.
No clues about the interior. And in fact, I think one of the reasons why we want to do black hole spectroscopy or understand precisely the motion of black holes is because we suspect that modifications of GR that are only important in the interior might percolate to the exterior and affect the way that black holes relax or the way that black holes move, for example, the dynamics of objects. So yeah, there's kind of an expectation, that might not be fulfilled, not to the precision that we're going to have in the next 50 years, but still it's there and it's important to explore that. Yeah, thank you. And in fact, that's also a good motivation for this slide, because we were given two gifts. Not only black holes in isolation are simple, black holes with companions also are simple. And we need companions if we are ever able to study black holes. A stationary, isolated black hole is not good to us because we can't have access. We can't get information from it. So we need some sort of dynamics, either accretion disks moving on the exterior of the black hole, or this guy having a companion that makes it move and makes it generate gravitational waves. Now, if you place a companion close to a black hole, then a number of things are going to happen, right? First of all, if this guy is moving, there's going to be spin-induced multiples, but uniqueness theorem takes care of those. But there's going to be tidal heating because there's tides generated that are going to affect the motion of this guy. There's going to be tidal distortions of the geometry. And in general, they could be having precessing, highly eccentric motion. Now, two things, they're not magical, they come from the field equations, but two interesting things happen. The first is that black holes don't polarize in general relativity. So their tidal of numbers vanish. Okay, that's property number one. Property number two, even if you place them on highly eccentric orbits, gravitational wave emission quickly circularizes them by the time they reach the band of our detectors. One example is shown here in this plot below, where I'm evolving a black hole binary that starts with some eccentricity and some large semi-major axis. So suppose you have some common envelope stage, you form a black hole at a distance of 10 to the 7 Schwarzschild radii, and you just let it evolve. there's a common envelope, so there's matter around this, this black hole, which I parameterize by some density rho, okay? Now, dynamical friction on this binary initially tends to increase eccentricity. So you see, as the semi-major axis decreases, the eccentricity increases. But quickly, gravitational wave emission takes over and eccentricity goes down. So by the time we reach the detector band, which roughly corresponds to a semi-major axis of 20 or 50, eccentricities are really small. So in summary, you give me a black hole binary, it's quasi-circular, there's no tidal love number in it. It's a really simple binary emitting gravitational waves. That's as good as it gets, okay? Good. So there's a number of fundamental questions you could think of to answer. I'm just going to focus on two of them. First of all, can we know that we're looking at black holes from the gravitational wave signal? And do we know if it's a curved black hole? How can we go around, take a gravitational wave signal and constrain alternatives? And of course, I'm going to give you a half an hour summary of what we think we know, but the answer to this takes years and decades and requires understanding the theoretical framework, partial differential equation analysis, simulations, the modeling of the objects, observations, and data analysis. It's a really complex enterprise that takes really decades to perfect. Okay? Now, there's, I think, a number of different ways to attack this. I'm going to focus on a very specific program that I call the black hole spectroscopy program. And the idea is really simple. I'm not so much interested in the initial stage, how these guys move when they're far apart. I'm just going to look at the final stage, okay? And the final stage sees two compact objects merging, coalescing, and forming a single distorted black hole that's relaxing to the final state. Now, the uniqueness theorem tells me that here, at very late time, so by the way, this is wave amplitude as a function of time. So at late times, I should have a single curved black hole. That's uniqueness result. So if I move backwards in time, here, I should see myself looking at a slightly distorted curved spacetime, okay? So the idea is really simple. I'm going to try to understand what happens at this stage by expanding the field equations around a curved black hole. Okay, it's exactly the same procedure that we do to look at sound waves in the fluid dynamical equations, right? We take some average pressure and density, and we expand to first order the field equations. We do exactly the same. Now, when you do that to general relativity, you're going to find that all the metric components or curvature components can be combined into a single master equation. And that master equation, of course, obeys a linear second order partial differential equation that looks like this, okay? It's a wave-like equation with some non-trivial effective potential V, and I'm going to come back to this V later on, and it has some source term. Okay, the source term tells you what exactly is causing emission of gravitational waves, and psi encapsulates this combination, linear combination of metric quantities. Now, the usual way you have to look to deal with equations such as this, one of them is to look for the characteristic frequencies for the spectrum, or if you wish, you look at the poles of the Green's function. Okay, so you do a Fourier or a Laplace transform, and you turn this 1 + 1 equation into a single ordinary differential equation that looks something like this, and that you can formally solve in terms of a resolvent. this guy over here, okay? So the poles of this resolvent are called the quasi-normal frequencies, and the solutions psi are the quasi-normal modes, okay? Now this is in the Fourier spectrum. At the end, you're always interested in the time response, so you need to invert the integral, right? And when you think about frequency integrals, you can always close the contour, right? If you remember the complex analysis course, then the poles, the residue at the poles is going to give you the response. Here it is, okay? Of course, there's other contributions to the integral. The contributions from the poles are these guys over here. It tells you that the gravitational wave form H is a linear superposition of all the roots of all the poles of this Green's function. And the poles lie in the complex plane, okay? The solutions to the characteristic frequencies omega lie in the complex plane, and I decompose that, the response, into an exponentially damped component and something that oscillates, okay? So we know these frequencies f and damping times tau to an extraordinary precision. We know them to 20 decimal places just by solving this linear equation. Okay, and you see here that there's 3 indices. They are related. L and M are angular indices because we expanded the fluctuations in spherical harmonics. And if you think about the hydrogen atom, they always carry 2 indices. Okay, and in the same way as the hydrogen atom, for fixed L and M, there's a countable infinity of solutions, which I label as N, the overtone number. The dominant mode, the one that dominates the response, is the one which has a longer time scale tau. We call this the fundamental mode, okay? Now, let me be a bit more specific and give you numbers. This plot gives you the inverse of tau, so the imaginary part of the frequency, versus the real part, the oscillating part, okay? For L equals 2, the quadrupolar mode, and L equals 3, the octupolar mode. There's around 50 modes here, but of course, in practice, you only care about the first few, the fundamental mode. So for instance, the fundamental L equals 2 mode, you can barely see it. It's this dot over here. And you know it's a fundamental because it has the lowest imaginary component, therefore the longest lifetime. You can put this in numbers. For a 10 solar mass black hole, okay, this geometry rings at around 1 kilohertz, and it has a lifetime of 0.5 millisecond. Okay, so if you think about Copenhagen, it's an example I like to give. Think about Copenhagen, you disturb Copenhagen, and in around half a millisecond, it relaxes. It died, the fluctuation died off, okay? So it's, of course, a really highly damped fluctuation and mode because things travel at the speed of light and energy is quickly dissipated to infinity and to the black hole horizon. And actually, this is one of the big problems for people like me thinking about how to explore the black hole spectrum. Black holes don't really ring, right? They have quality factors of around 3. They really just relax. You know, if you think about the Earth or the Sun, these are good oscillators. Black holes are not good oscillators. They just relax with a thud. And that's it. They die off very, very quickly. Okay? Are there questions up to here?
I didn't see any so far.
Good. Let me continue then. So the idea now is very simple, right? We take a gravitational wave signal, we look at the relaxation stage, and we try to fit it to these modes. We know these modes. If you go to my webpage, there's tables of these guys. And the idea is to try, first of all, to find the mass and spin of the black hole, because you see, one dot, one mode actually means two quantities, the lifetime and the vibration frequency. But the modes depend only on mass and spin. So with one mode, you can extract mass and spin. With two modes, if you're lucky enough, you can actually test the theory. That's exactly what LIGO did. The first black hole spectroscopic test. And here it is. Black solid line is the 90% posterior distribution of the mass and spin, or if you wish, of the decay of the time scale and frequency of these modes. The idea is really simple. You take the entire signal, this signal over here, and you fit it to your best simulation possible. That's going to give you a mass and a spin. From that mass and spin, you go to my tables, you extract time scale and frequency, and these are the lines, okay? Now, you do spectroscopy. You go to the final stage and you fit it to an exponentially damped sinusoid. And of course, if you get the LIGO data, the first thing you'll think is, well, this is great, but where should I start? Okay? It depends on the start time for the fit, and here's the results as a function of different starting points after the peak of the waveform. So purple starts fitting 3 milliseconds after the peak, red 5 milliseconds, and so on. And you see that they all include the total waveform predictions. It's a beautiful agreement. But you also see that if you start fitting too early, 1 millisecond, you start getting in spiral imprints. You start getting things which are actually not a distorted black hole. So at very early times, you don't find agreement, okay? Errors are really large. Well, are large. But you have to remember, this is the first measurement of a black hole mode, a fundamental mode of a black hole, a characteristic frequency. It's an amazing plot, in my opinion. The signal-to-noise ratio in the ring-down portion, in this relaxation stage, is of the order of 7. It's marginal detection, okay? So let me show you where we're going to be 10 years from now. When upgraded versions of our Earth-based detectors start working, and you have a signal-to-noise ratio of 40, for example, this is how it looks like. This quadrupolar mode that I showed you now is going to look like this. The uncertainty in the frequency and time scale become much, much shorter. In fact, with signal-to-noise ratios of 40, you see a second mode. You see the octupolar mode. So you're going to test general relativity, okay? It's not only now a consistency check of calculating mass and spin, it's actually a test of GR, okay? This is for signal-to-noise ratios of 40. LISA, when it flies, will see signal-to-noise ratios of thousands. I can't even show that on the plot. It looks like a dot, all of them, okay? So black hole spectroscopy is starting in our lifetime. It's really going to be an amazing tool. Good. These are all predictions from the linear theory, but there's much more to general relativity than the linearized version. If you start thinking now about the entire chain of expanded equations, think about the second order. When you start expanding the field equations to second order, you're going to find an interesting thing. First of all, you can still encapsulate the second order quantities in a master wave function that I'm calling psi2, the second order quantities. And now these are sourced by the first order, so the linearized wave functions, the square of them, okay? So if you think about the ring down stage, psi1 is an exponentially damped sinusoid. the square of an exponentially damped sinusoid, well, it's roughly an exponentially damped sinusoid with twice the frequencies, right? And therefore half the lifetime. So are these nonlinearities present in the waveforms? And I think until a year ago, the statement was, no, we can't see any nonlinearities because the horizon eats them all up. And this is not true. There's now different groups, Caltech, Princeton, and NBI, that have seen, Johns Hopkins as well, that have seen these nonlinearities. Okay, and the idea is really simple. You start colliding black holes, either head-on or quasi-circular, and you start looking for modes which have a residual imprint on twice the linearized frequency. Okay? This is one example. We take head-on collisions of two black holes at varying center of mass energy. So there's a knob that I can tune in, which increases the energy. The knob is very interesting and important because it gives me a handle on the nonlinearities in the process, okay? So you could imagine that as I start colliding these guys at higher and higher energy, the ring down amplitude, the first order ring down amplitude starts going up, and the nonlinearities also start going up. And what I show you here is the amplitude of the nonlinear mode. I'll explain what this means, as a function of the amplitude of the first order linearized ring down mode. Okay, so take, for example, a linear quadrupolar mode, L equals 2, M equals 0. When you square a quadrupole, an L equals 2 harmonic, you get, among others, you get an L equals 4 harmonic. So I'm measuring the amplitude of the L equals 4 nonlinear mode, okay? And what you get is a beautiful quadratic curve. The amplitude of the nonlinear mode depends quadratically on the amplitude of the linear mode, exactly as you expect from this structure of equations, with the correct frequency, okay? We have since repeated this for quasi-circular in spirals, and you get exactly the same type of quadratic behavior. It's a beautiful set of results that we've got in the last half a year or 1 year, okay? In fact, you can quantify this. If you define this ratio, the nonlinear ratio, to be the ratio between the amplitude of the quadratic mode to the square of the linear mode, this will be kind of a universal number. For non-spinning binaries, quasi-circular non-spinning binaries, the ratio is of order 0.16. It's small, but not hopelessly small. Okay, we will be able to measure this when we have good enough detectors like LISA. Let me tell you that it's also impressive that this same number was recovered from near horizon symmetries, or the so-called Kerr-CFT, that makes use of an extremal or quasi-extremal geometry. Okay, they get up to the same digits, like this number, and there's a mystery here. I don't think we understand this to any level, because these Kerr-CFT predictions should be valid only for non-spinning black holes. Sorry, for highly spinning black holes, where this number is valid for black holes spinning at roughly 70% the maximum possible value. So of course, the next question is, what happens to these numbers when we change the black hole, when we change the initial conditions? So we did this study a few months ago, and this is what we get. And by the way, our results agree with the Princeton Caltech results, also just came out. This is the ratio. So what we do is we look at second order perturbation theory. We take a black hole of fixed spin 0.3, 0.7, 0.95, and we throw a Gaussian wave packet of width W. Okay? The first thing that you see is that the ratio, this nonlinear ratio, depends very weakly on the initial conditions, on the width of your wave packet. Okay? The second aspect is that it depends weakly, but non-trivially on spin. Okay? In fact, at fixed width, this is what we get for the ratio as a function of spin. So it goes down from 0.16 to something like 0.08 at spins of 0.95. So there's a non-trivial dependence which raises some doubts on this Kerr-CFT, on the application of Kerr-CFT predictions to this type of mergers. I think there's a lot more that needs to be understood. It's a beautiful direction, but we need to understand a lot about these results. Okay. If there's any question, just let me know.
Can I ask one?
Yeah.
So far the calculations are only still based on the 2-2 mode, right?
Yeah, the calculations are based on the 2-2 mode, giving either a 4-4 or a 0 memory term. Yeah, because that's just the most important mode.
Okay.
Thank you. In fact, it's clear that the next step is going to be to understand if there's any interesting structure in other modes that we can detect eventually, yeah, especially in the near extreme regime. Okay, so this was spectroscopy of single isolated black holes. And one of the questions that I'm sure we all have when we start thinking about this is if we can excite resonantly the modes of a black hole. Now, the modes of a black hole are localized close to what we call the light ring or the photon sphere, okay? And in the light ring, matter moves at the speed of light. And that also immediately tells you that it's non-trivial to excite these modes, okay? You need something that's high frequency. And isolated matter, like a star or a planet, just can't reach the light ring. They just plunge into the black hole. Okay, so exciting with isolated objects, a black hole is not going to make it. But you can think of other ways. You can think of having a tuning fork with the frequency of the light ring of your black hole and, ringing it close to the black hole. Of course, nobody's going to do that. But you can take a small binary, this object over here, evolving by gravitational wave emission, and therefore sweeping the orbital frequency from low to high frequencies until it locks in to the resonant frequency of a black hole. Okay? Can it resonantly excite the modes? Here's the results. I'm showing you the fluxes of gravitational radiation as the small binary evolves. So omega naught is the orbital frequency of this small binary. And the way we model this is really just taking linearized Einstein equations with a source term describing two point-like particles evolving over time. Okay? Now, the red line here tells you the ratio of the flux to the Newtonian prediction. The gray line tells you the flux of energy at the horizon, and this black solid line is the flux at infinity. And it's super clear there's resonances in the system, so you are exciting the modes of the black hole as soon as you lock into the frequency of a quasi-null mode. Okay? For instance, the ratio has a local peak when you tune in to the 3-3 mode of the black hole. Or you see even more clearly at infinity, small localized peaks at each or close to each of the quasi-null modes of the black hole. It's not an intense amplification. You see, ratios go up to 2.5. It's not impressive. But that's because this black hole is spinning at roughly 0.9. Quality factors are of order 4 or 5. If you make the black hole near extremal, this ratio can be arbitrarily high. Okay? But you do get it. In fact, you can even think about the modes not of isolated black holes, but of binaries. You take a black hole binary and you ask the question, does the binary have a spectrum in the way that a molecule has a spectrum? So you take two hydrogen atoms, this molecule has a spectrum. Do black hole binaries have a spectrum? Now, because the spectrum of black holes is related to null geodesics, you might think about trying to discover closed null geodesics in black hole binaries, okay? And I was very happy when I started doing this because there's an exact analytic solution called the Majumdar-Papapetrou solution that tells you the space-time geometry of extremally charged binaries. And if you look at closed, so these are static black holes. If you look at closed null geodesics, you will find they come in three types, and they are here. First, each of the black holes is surrounded by a quasi-circular null geodesic. This corresponds to the null geodesic of isolated black holes. Okay? But then we found two other types of null geodesics. One is this guy, a global null geodesic, and the other is an H-shaped geodesic. I was delighted when I found this. I thought, man, I'm the first person that knows this happens, and this must mean that binaries must also ring the binary itself. Unfortunately, a week later, I discovered that Chandrasekhar had understood all of this before me. Okay, didn't diminish the pleasure, but it's still interesting to see that already in '89, he understood a lot of this for the same extremely charged black holes. So we did something else. We took a black hole binary, and now instead of studying null geodesics, this is really just a high frequency regime, we actually studied wave dynamics. So I'm going to take a black hole binary and I'm going to throw a wave packet of gravitational waves at this system. Okay? This is what you find. I'm throwing a spherically symmetric pulse, or almost spherically symmetric pulse of waves, the driving mode, the blue line, and the response, the scattered wave, is going to come in a variety of modes. The dominant modes are a 2-0, so L equals 2, M equals 0, and a 2-2 mode. Okay? And we started varying the initial data, the width, the location of this initial pulse. And we always saw the same characteristic ring down, the relaxation stage at the end. This seems to say that indeed, black hole binaries have proper oscillation modes. And who knows, they might be resonantly excited. So go here, for example, take one of these black holes surrounded by an accretion disk. Okay, the accretion disk has low frequency for this black hole, but it might be tuned to the global frequency of this mode. So I cannot exclude at this stage that we can resonantly excite the modes of black hole binaries. It's a very exciting prospect. Okay? Good. So I'm going to finish this by telling you about what we thought we knew and we realized we don't, which is this stability of the black hole spectrum. Now, any black hole spectroscopy, or actually any spectroscopy program, can only be done if, when you start varying infinitesimally the initial conditions, your results also vary infinitesimally. This means I calculate the spectrum of a black hole in vacuum. It should better be very close to that with a tiny amount of matter close to it. Okay? So we started trying to understand this, we and many other people. And one of the things you can do is you go to the effective potential. You remember there was V, this effective potential governing linearized fluctuations, and you add a small bump to it. This small bump has a height epsilon and a width sigma, and is placed a distance a away from the black hole. So if we ever want to do spectroscopy, we hope that the quasi-normal spectrum, the poles of this ring function of this disturbed potential are epsilon close to the vacuum case, okay? Well, to our surprise, we found results such as this. So we take an epsilon 10 to the minus 6. This means, let me go here, that there's a bump here, which is 1,000,000 times smaller than this bump, okay? And I place this bump a distance a away from the black hole, which I start varying. So I measure, this is the spectrum, and now I start varying the distance. 40, 45, 50, 55 Schwarzschild radii away from the black hole. Okay? And what you see, well, this is obvious. It's obviously destabilizing the spectrum. Okay? You have something which is tiny, you're placing it farther away, and the black hole spectrum is being modified by an arbitrarily large amount. And of course, this should be cause for concern. It is a cause for concern, but we understand a fraction of this problem. A fraction of this problem lies that what we actually see is not directly related to the spectrum. We don't see Fourier domain things, we see time domain things. And in the time domain, the waveform looks like this. So I have my black hole with a tiny bump far away, and I'm going to scatter a wave, okay? Black dashed line is the vacuum, isolated black hole signal. Blue line has a bump of 0.1 at a distance of roughly 30 Schwarzschild radii. And the important thing is that initially, the initial response is indistinguishable from the pure vacuum case, okay? So differences only set up at late times. And we know what's happening. What's happening is that this bump is actually creating a cavity that filters low frequency waves. So it retains low frequency waves, which cannot tunnel out of this bump, and lets only the high frequency waves pass. So at late times, what you end up with is a low frequency signal that's trapped in the cavity and is slowly leaking out, okay? So the problem is spectrally unstable, but in the time domain, the impact that it has on the waveform still scales with epsilon, okay? So it's still perturbatively small, okay? Now, this was an artificial bump, but there's many ways, many physically interesting ways where it can appear. One of them was actually an idea by Shinji, Naritaka, and Kazufumi. It's a very interesting idea. You take, instead of one field, you take a theory that couples two scalar fields. This is the theory, okay? The only thing you did is you have a kinetic term for the fields, and now they're talking to each other in some type of this formal coupling, okay? And what happens is that the effective geometry seen by the field chi or by the field psi are different. In particular, the field chi sees an horizon which is larger than the horizon probed by the field psi. Okay? It's a beautiful example of the things we've been discussing, because now the field psi probes the interior of the horizon of chi, but it couples to chi. So that information can leak out to the exterior of chi and therefore to our detectors, okay? And in fact, we find a number of interesting things which I don't have time to discuss. You can look at the preprint, but the important thing for me is the signal itself. If you look at the relaxation signal, you're going to find that it has two components, just like the bump signal. A high frequency signal, that's the prompt emission from the interior of this horizon, or if you wish, from the smaller light ring, and a low frequency component, which is the relaxation of the exterior horizon. Okay? So it's a very simple implementation of this spectral instability, something that could happen. We should be prepared for this. Okay? In fact, there's an even better known example where this is going to happen. If you give me a black hole, it's surrounded, a charged black hole surrounded by plasma, you get exactly the same thing. The plasma prevents low frequency electromagnetic waves from propagating, so it's creating kind of an horizon for electromagnetic waves. But gravitational waves travel through, okay? So when you look at the ring down of a gravitational wave in this setup, it carries an imprint of the electromagnetic signal, of the electromagnetic conditions, and of the gravitational wave conditions. This is how it looks like. So these guys are going to be modulated because of the environment. So there's another simple implementation of spectral instability, okay? I think I have 5 minutes. Let me give you a final example of spectral instability when you start placing a bump not far away from the black hole, but very, very close to the horizon. You have to remember that there's a lot of time, if you wish, close to the horizon. So if you change the boundary conditions, because you are adding structure, either because you have firewalls or something, some quantum field theory response close to the horizon changes the local structure of the space-time. If you change the boundary conditions, well, the disturbed light ring is going to create a signal that travels to you, but a fraction is going to interact with this structure, okay? So anything that does not have an horizon eventually needs to come to our detectors. And the universal response looks like this. The prompt light ring emission, this signal over here, okay, has to be followed by a sequence of copies of the initial burst. We call them echoes because really they are echoes of the initial burst. And the idea is exactly the same as with the bump. You have a cavity that's cleaning your signal of the high frequency components. It lets the high frequency go. It keeps only low frequency things. It's a universal response in the sense that the delay between echoes only depends of where you put your structure in, okay? Now, if we're looking for new physics, I think we need to be aware of these aspects. And I think it's kind of fun to think that animals like dolphins, they actually move around based on this. It's a sonar technique that actually looks for echoes in the signals that they emit. So I am sure that if dolphins can do this, we sure as hell can search for echoes in waveforms, and it would be an amazing prediction that goes well beyond what Einstein is giving us, okay? So I think I'm going to finish here by telling you what I think is the main message. Gravitational wave astronomy, it's an amazing tool, and it's going to become a precision discipline. We're not there yet, okay? But the 10 years that come for all of us are going to be changing the field. We are going to be doing precision spectroscopy. We are going to be doing precision searches for tiny differences in the motion of compact objects. I told you about a couple of things that we know we can do, but I am sure that there's a number of tools to explore gravitational wave astronomy in ways that we don't know yet, and that's going to be up to you. So it's a very, very exciting field. I'll stop here. Thank you so much.
Thank you very much. Is there any questions in the audience? Okay, so I see one hands up. Zofu.
Hello, can you hear me?
Yeah.
I have a very simple question. I also working on the binary black hole around the supermassive black hole. This is triple system. I see you see the gravitational wave from the binary black hole can induce the supermassive black hole's quasi-normal mode. So I have a naive question: how do you distinguish the gravitational wave is from the binary black hole or from the supermassive black hole and the surrounding by the stellar mass black hole?
I don't know. The answer is I don't know. So what you're going to get, so there's exciting things, but there's a lot of work to do. So the exciting thing is that you could do multiband astronomy, right? You could, in principle, detect motion from the center of mass of this binary in a low frequency detector like LISA, and the high frequency component of the binary itself in LIGO. But your question is a bit more specialized, is how do I know, for instance, that this is going around a supermassive black hole? And for that, we need to be more sophisticated, because the motion, the way right now that we have to model this small binary is really a poor way, right? We just model it as if it's in isolation. A set of 2-point particles following a quasi-Newtonian motion on each other. So I think we need to go up in PN order. When we place it around, we need to know the equations of motion of this guy, okay? And only then you can start looking for low frequency change, low or high frequency changes to the signal relative to an isolated component. I mean, I think this is an exciting thing. At some point in the lifetime of the binary, you should have announced emission, but this, I am afraid, it's not going to be a generic consequence. I mean, most of the life of the binary is not spent exciting the modes, right?
Okay. Yeah.
Yeah. So if you're working on this, I think the next step is to improve the modeling of the motion of these small binary components, in my opinion.
Okay. Yeah. We also have established a kind of a possible solution for this motion, but even for this,
That's very interesting. Then I would like to know more about that. Yeah.
yeah. But even we know this, because I have seen your paper about this, I don't. I'm not sure this the quasi normal mode is only from the supermassive black holes also, or have you combined the binary black holes gravitational wave? That's my question.
Oh, I mean, I don't think you can. So if I guess your question is this really just the modes of the supermassive black hole or also of the binary? Is that the question?
Yeah.
I don't think it's easy to separate source. I mean, the only thing I can tell you is here you're keeping the source fixed, right? Or if you wish, you're keeping the black hole fixed and you're changing the source frequency. It's natural to say that these are modes of the central supermassive black hole because they align very well with the modes of that black hole. But you really can't separate. I mean, you can't separate the object that's exciting from the object that's being excited. But maybe we can follow this up by email. I would be interested in knowing what you're doing exactly.
Okay. Thanks.
Thank you.
Any other questions? Maybe I can ask one. So in the case of, in the case of cavity and also the echo scenario, how do you make sure that the modes generated within, trapped within the cavity, they do not accumulate and cause instability?
Um, Good. So your question is why? So let me go here. Why the mode is not accumulating and producing instability? There's nothing. So if you do this with a source, we looked into that actually. It's a good question. But if you try to do that with a source, so you try to fill the cavity, let's say. Okay. So for instance, you start sending waves. Yeah, you just start, you shine a lantern on this system and you start filling the cavity. What's going to happen is that after a certain amplitude of the signal, the cavity fills up and then the rest just dissipates very quickly. So the cavity, because you see, there's a finite height here, the cavity cannot hold an indefinitely large amount of energy. The only way you could make that happen would be to find some way that this cavity is extracting energy from somewhere. This can happen, but it requires ergo regions and no horizons. You will have an instability there, but it's slightly of a different nature. It's an ergo region instability. Yeah, but like this, it's not going to happen.
Because this kind of potential well reminds me of, you know, when you have when the space-time have stable photon rings, it is kind of conjectures that the space-time will be unstable because of the accumulation of modes, right? So I think that depends on.
I agree with you. I agree with you. The light. So first of all, it's a conjecture because it should only come at second order in fluctuations. And second, it's a high frequency instability in the sense that it was seen in the iconal modes, if you wish. So high frequency modes live very, very long in those spacetimes you're referring to. This is slightly different because it's a low frequency kind of cavity. The high frequency modes just go away. The low frequency stay here. So it's slightly different, but they are related, I agree. And I do not know if this cavity gives you a second order instability. Yeah.
Okay, thank you. And okay, so if no question, maybe we can stop here. And if you want to connect with Professor Cardoso, you feel free to just chat with him through emails. And I think he will be very happy to answer any questions. So so at the moment, let me stop recording.